Hello and welcome to the second in a series of short talks about electromagnetism. First thing I want to do this time is show you a quick video. Okay, we have here a gentleman who is taking a wire and a compass, placing the wire on the compass and then attaching a battery to the wire. This is going to result in a current flowing along the wire. And you'll see that when the current starts to flow, the compass needle deflects. And compass needles only react to magnetic fields. So this was the first evidence that currents causes magnetic fields. Put the compass on top of the wire and it deflects the other way. And this gives some clues about the direction of the magnetic field. Right. That's enough of the video to give you the idea of what's happening. Currents cause magnetic fields. A whole series of more delicate experiments reveals what the direction of the magnetic field actually is. And the magnetic field occurs in a circular pattern around the current. It's not a terribly good drawing, perhaps, in 2 dimensions. The idea is that the magnetic field is, if the current was going sort of along this pen straight towards you, then the magnetic field would be going around the pen like this, at right angles to the current. This effect was quantified by Jean-Baptiste Biot and Félix-Savart and has become known as the Biot-Savart equation. This gives you the contribution to the magnetic field at P from a small length of current flowing in a wire here, a distance r away from P, and the direction of the current subtending an angle theta at P. The direction of the current is perpendicular to the plane containing both the wire along which the current is flowing and the point P. So in this 2-dimensional drawing here, the magnetic field is either coming straight out of the paper or going straight into the paper. You can tell which way it's going using the right-hand screw rule. The right-hand screw rule is as follows. Take your right hand. Put the thumb in the direction that the current is flowing, in this case this way, and clench your fingers in a fist, and then the direction of your fingers, that is the direction that the magnetic field is being generated in. So in the case of this current flowing up here, my fingers above the current are coming towards me, which is out of the paper. So the magnetic field at P would be coming out of the paper. Later on, you'll be asked to integrate this along straight lines to work out the total magnetic at P caused by a current flowing along a straight conductor. However, we haven't quite done the maths required to be able to do that integral yet, so I will leave that for a future module. All we're going to do in this module is simple cases where we can make approximations and the angles and distances are much easier to work out. This is more the standard of calculation that we're doing in this introduction talk. Remember the Biot-Savart equation, delta H equals mu naught over 4 pi r squared times the current times delta L times sine of theta. And we're applying it here to a loop of current of radius r, and we're being asked what is the magnetic field in the center of this loop of current. To do that, we just have to add up the contributions from all of the little lengths of wire delta L all the way around the loop. First thing we should work out, how many delta L lengths of wire are there around this loop? And the answer is, well, the total distance around the loop is the distance around the circumference of a circle, and that's 2 pi times the radius r. So, how many little lengths delta L are there in 2 pi r? Answer, 2 pi r divided by delta L, little lengths of delta L. What is the effect of each of these lengths delta L? Well, let's consider this one here. You'll notice that the angle, this angle here, theta, is 90 degrees for all of these little lengths delta L, which is why I haven't bothered to put sine theta on the formula on the slide. Theta is always 90 degrees, which means sine theta is always 1. So that's easy. R is constant. All of these little lengths are the same distance away from the centre. That's just the radius of the circle. That's good. The current we know how many little lengths delta L there are, and we know that they will all have the same effect, because they are the same distance carrying the same current at the same angle. So all we have to do is just multiply that by the number of little lengths delta L there are. And our total H field would be mu naught divided by 4 pi r squared times the current times delta L. Sine theta is just 1 for 90 degrees, times the number of little lengths of delta L there are. That r cancels with one of the r terms down there. The pi's cancel. The 2 and the 4 would just lend you a 2 down at the bottom. And we'd have a formula that the total H field, magnetic field in the middle of the circle, would be mu naught times I over 2r. In this case, we're told that the current is 20 amps and the radius is 10 meters. So the answer is just mu naught. The constant known as the permeability of free space. And that's about the hardest calculation of magnetic field that we're going to be attempting in this module. They do get harder later. Other question. In what direction would this magnetic field occur? Well, in order to know that, we need to know whether the current is going clockwise round this loop or anti-clockwise round this loop. You can see in the illustration on the slide that, assuming that I've got my drawing in reasonable perspective, what I'm trying to illustrate there is a current that is flowing around like this, anti-clockwise. Another example of the rule, everything goes anti-clockwise except clocks. So if the current is flowing anti-clockwise around this direction, I can use the right-hand screw rule, take my right hand, put my thumb along the direction the current is going, and look and see where my fingers are going. That rotation of my fingers would come up from the center of the coil. So the answer is A. The magnetic field would point straight up. If the current was going in the other direction, it would be going down, B. It would never be in the direction C or D. Okay, that's enough for this one. Next time we'll revisit Faraday's law and have a look at inductance.